a single atom. So you get a valence band, and then an energy gap, and then a conduction band. And when there's no, when electrons aren't excited, there's no energy, then the highest energy electrons will stay in the valence band. But when you have any light, any temperature, anything that will excite the electrons, some will have enough energy to leave the valence band and go to the conduction band. And when they do that, they'll leave behind holes, which are positive, and the electrons are negative. Now, semiconductors can only absorb light that has a higher energy than their energy gap here. So if light comes along that does have a higher energy than this energy gap, these electrons in the conduction band will get excited, and then will slowly start to lose energy and recombine with holes in the valence band. Now, in order to lose that energy, they release energy in terms of photons, or light. And the light that's emitted has about the same energy as the energy gap. So we built a structure to enhance the radiation of this light being emitted, and the main way to do that is with these antennas. So our structure starts with a glass base, and then an adhesive called epoxy. And epoxy and glass work really well together because they have about the same refractive index, which means when you shine light on it, it won't reflect in a lot of different directions, and that would mess up the measurements. So then we have our semiconductor, which is indium gallium arsenide, and that's a good semiconductor because it's a 3,5 compound, meaning it's from the 3rd and 5th group of the periodic table, and those are the best for emitting light, or photoluminescence. And then we have an antenna here, and the antenna is made out of gold. We use gold because it's the most conductive element besides silver, and we don't use silver because that oxidizes. So now I'm going to explain a little bit about how we get our antennas on our substrate. So we start here first with putting a chemical called e-beam resist. E-beam resist is very sensitive to electron beams. So when you shine an electron beam, you'll change the properties in the resist. And so then when you expose it to a chemical called a developer, the part of the beams that you hit the resist with, those parts will then dissolve, and so you'll get this pattern here. And the machine that controls these electron beams is called an electron beam lithographer, and they use electron beams because electrons travel in waves that are shorter than light, and so that allows for a higher resolution. And the other thing is, since they're shorter wavelengths, you can control the beam better. The beam of electrons comes out through an opening or an aperture. Now when the electron beam hits the resist, the energy from the electrons transfer into the atoms in the resist. And the longer the atoms will scatter around. And the longer you expose the beam, the more the atoms will scatter, and that destroys the resolution. So you have to be careful of the exposure time that you leave the beam onto the photoresist, or the e-beam resist. So the next process is called electron beam evaporation, and this is how we actually get the gold to make the antennas on. So we put our substrate up here, and we have a crucible of gold here. And we heat the gold up with electron beams, and so then the gold will evaporate and recondense on the substrate. And before we do that, we actually evaporate a little bit of titanium as an adhesive. And this is all done in a vacuum to keep everything nice and clean. So kind of an outline of the whole process. First, we have our resist on our substrate. Then we do lithography, expose it to this other developer chemical, so you get this pattern here. And then you evaporate the gold, which is the black, and then you expose it to another chemical called acetone, and acetone will take away all the rest of the resist and what's ever on the resist. So you're left with these black triangles here, or rectangles here, which are the gold antennas. So now I'm going to explain a little bit about how the antennas enhance the radiation of light emitted from the semiconductors. So excited semiconductors can also be modeled as a dipole. Here, oscillating dipole, so that means just kind of two opposite charges. and those charges create an electromagnetic field. And the electromagnetic field will induce the antenna, the electrons in the gold antennas to start oscillating back and forth too. And the frequency of these waves going back and forth in the antenna are the same as the energy gap from the semiconductor. So it's a fixed frequency that they're oscillating at. And it turns out that you want waves to be oscillating back and forth of a distance of half their wavelength. Now this dipole right here is very small. It's only about 4 angstroms. And that's way too small for the waves that are being emitted. So we place our antennas. This distance is exactly half a wavelength. And that's the perfect distance for the waves to be oscillating back and forth at. And that creates a resonance structure. And that's how the radiation is enhanced. So my project was actually to use a little bit of a simpler antenna. This is just on one plane. And I was playing around with this gap distance, or the distance between the two antennas. And so I used some computer simulations, and these are pictures of the computer simulations. This is the average magnitude of the power radiated over time. So this one here is just has an antenna with a gap of 3 nanometers in between. And this one is just a plain dipole. And so red is more power and blue is less power. And so you can see that the antennas really make a big difference with the color. And it's actually 34,000 times more than just a plain dipole. And so that is actually the top one here from a distance of 3 nanometers. But I tried a bunch of different distances actually, a gap distance of 30, 20, and so on. And as you can see, the closer or the smaller the gap distance, the more total power radiated. And so I'll explain a little bit about why a smaller gap distance the better. So it turns out that this dipole, the electromagnetic field that it creates, the antennas don't capture all of that field. And so the closer the antennas are together, the more of the field they're able to capture. And that leads to more radiation resistance. Resistance is basically just energy dissipated from opposition to the passage in electrical current. But radiation resistance, and so normally in like a circuit that would be heat being emitted, but radiation resistance produces electromagnetic waves or light. So we want to maximize the radiation resistance. The closer the better. It maximizes the radiation resistance, and current squared times radiation is power, so the more radiation resistance, the more power. So I want to thank everyone in Sharp, and especially my mentor, Kevin. So. Questions? Yes?
Do you know whether decreasing the gap between the two antennas to less than 3 nanometers, were you able to simulate that? Or?
Yeah, so that, we think that would also make more and more power. The only thing is that one problem is the smaller the gap denses, you also get more capacitance. That's another element in the circuit. And the capacitance changes the resonance a little bit. So then you have to tweak the other dimensions in the structure too.